Welcome back to our YouTube channel. My name is Teacher Mati, and today we're going to look at linear motion, and specifically we're going to look at speed. So speed is simplified by small v. So when you see small v, that one is speed under linear motion. So let us go direct to the definition of speed, and we want to know what speed is. Basically, speed refers to the distance covered per unit time, and the SI unit of speed is given by meters per second. So meters is the SI unit of distance, and seconds is the SI unit of time. Let us look at this particular example. A body covers a distance of 20 meters in 4 seconds. It rests for 10 seconds and finally covers a distance of 90 meters in 70 seconds. Calculate the average speed. So we are given a displacement of a body in 4 seconds, and that displacement is 20 meters. The object rests for 10 seconds and continues to move a distance of 90 meters in 70 seconds. So we are supposed to calculate the average speed. So average speed is given by the total distance divided by the total time taken. So the total distance, we can just find it from this question. It's 20 meters as the first distance, and the second distance is 90 meters. The total time taken is 4 seconds for the first 20 meters, then plus the time this body rests, that is 10 seconds, plus the time it uses to cover the 90 meters distance. So it is the distance is given by 20 meters plus 90 meters, that is 110 meters, and the time is given by 4 seconds plus 10 seconds plus 70 seconds, and this one gives us 84 seconds. So we substitute these values in this formula, and we will get the speed to be 110 meters divided by 84 seconds, and that one gives us 1.3 meters per second. So 1.3 meters per second is the average speed of this body. So I want us to look at the next aspect that is very important, and that is acceleration. So acceleration is denoted by small a. So wherever you see small a under linear motion, that is acceleration. And acceleration by definition is the change of velocity per unit time. When we have the change in velocity, we mean we have the initial velocity and the final velocity. Initial velocity can be even from rest, and the final velocity can be the velocity at a given value, and also we can have the final velocity at rest or the initial velocity at a given higher value. So it depends on how the question reads. The SI unit of acceleration is meters per second square, and that is the formula we use. Acceleration is given by the final velocity, which is represented by small v, minus initial velocity, which is represented by small u, divided by the time taken. So let's look at this question. The velocity of a body increases from 72 kilometers per hour to 144 kilometers per hour in 10 seconds. Calculate its acceleration. So we have a body increasing from 72 kilometers per hour. 72 kilometers per hour is our initial velocity, and it increases to 144 kilometers per hour, which means that 144 kilometers per hour is our final velocity, and the time taken for this change in velocity is 10 seconds. We are supposed to calculate the acceleration. So the first thing is to make sure that everything is changed to SI units. Because the SI unit of velocity is meters per second, and we are given time in seconds, it is good for us to convert the 72 kilometers per hour and 144 kilometers per hour into meters per second, and that one we multiply 5 divided by 18. So initial velocity is equals to 5 divided by 18 times 72, then we convert it. It becomes 20 meters per second, which is the SI unit of velocity. So small u, as I said, denotes the initial velocity. So in terms of meters per second, we have initial velocity as 20 meters per second. Our final velocity, we apply the same formula. It's 5 divided by 18. We multiply by 144. We get 40 meters per second. Now we have final velocity and initial velocity. We just substitute the values in this formula. And by substituting, we get acceleration is given by 40 meters per second minus 20 meters per second divided by 10 seconds. And we get our acceleration as 2 meters per second square. So that is all about acceleration. Let us look at the second example. A car is brought to rest from 180 kilometers per hour in 20 seconds. What is its retardation? So we have the keywords here. When we are looking at linear motion, we must be able to identify the keywords. For example, when we see the word rest, the rest means that there was no motion and the speed at this point is 0. So our initial velocity of this car is 0. So the car is brought to 0 kilometers per hour from 180 kilometers per hour. So 0 is the final velocity. Then 180 kilometers per hour is our initial velocity in 20 seconds per given time. What is its retardation? So retardation simply means deceleration. And we are using this word because the car is being decelerated from a higher speed to a lower speed, in fact to 0. So we apply the same formula. We convert first 180 kilometers per hour to meters per second, and we apply the same formula. So our initial velocity is 5 divided by 18 times 180. We get 50 meters per second. So 50 meters per second is our initial velocity, and our final velocity, because the car is brought to rest, our final velocity is 0 meters per second. So applying the formula, acceleration is initial velocity, so final velocity, so our final velocity is 0 meters per second minus 50 meters per second divided by 20. We get acceleration as negative 2.5 meters per second square. Now the negative in this case implies that there is a decrease in velocity. That's why we have a negative. But if you are asked to give the value of retardation is 2.5 meters per second square. So the two values, the two answers are correct, but for the first one it shows that there is a decrease in velocity. So the next thing we are going to look at is motion time graphs, and the first one is the distance time graph. So we are going to plot a graph of distance against the time taken for moving object, and let us consider the following data. We have S to represent distance. Remember, in linear motion we use capital S to denote distance covered or displacement, and small t to denote the time taken. So we have the distance is not changing. We have 15 15 15, so meaning at 0 seconds the body was at 15, and for 5 seconds the body was still at 15. At another 5 seconds to make it 10, the body was still at 15. So there is change in time, but there is no change in displacement. So how can we plot that graph? We have the y-axis to take a displacement. So displacement, we take the y-axis, and at this point is where 15 is. We have the x-axis, so time, we take the x-axis. I'm going to 1 square to represent 5 seconds, another square, we add 5 to make it 10, we add 5 to make it 15, and we add 5 to make it 20. So this one, the x-axis, will be taken by time, and remember time, the SI unit of time is seconds. So we're going to plot these points. Where there is 5, take 15. Where there is 10, we plot against 15. So we're going to have it like that. So that is 5 against 15, 10 against 15, 15 against 15, and 20 against 20. So another important thing you're going to do is to plot a line that passes through the center of those points. So we have a line like that. So as we can see, the line is horizontal, and this means that our object is stationary. So this is the distance time graph of a stationary object. So also let us consider the following data. We have distance against the time. So but now for this case the body is changing the position. So we have at 5 seconds the body was at 10 meters, at 10 seconds the body was at 20 meters, at 15 seconds the body was at 30 meters, and at 25 seconds the body was at 50 meters. So you can see the body is changing distance uniformly. We have 10 moving to 20, moving to 30, moving to 40, moving to 50, and the time is still uniform. So after 5 seconds it is 10 meters, and after 5 seconds it adds another 10 meters. So the body is changing position uniformly. So we plot this graph. So we have the y-axis to take distance to take the y-axis, and the time to take the x-axis. So we plot that graph. So one square in the x-axis to represent 5, 10, 15, 20, 25, and for the y-axis we'll be having 1 square to represent 10. So this is 10, 20, 30, 40, 50. So we plot our points like that. So that is 30 against that is 15 against the 30, 20 against the 40, and the 25 against 50. The next thing is to draw a line that passes through the centers of all those points like that. So we have a line passing through the origin and having a uniform slope. So that means that the body is changing the position uniformly. When we have a line like this, we mean that the body has a uniform speed. So the body is moving at a uniform speed. So this is the distance time graph of the body that is moving with the uniform speed. So also finally, let us consider the following data. We have distance against the time. We have 5 seconds, 10 seconds, 20, 15, 40. You see, as we can see, now the body is taking the shortest time to cover a longer distance, meaning there is non-uniformity in terms of speed. So we're going to plot a graph. We have the distance to take the y-axis and the time to take the x-axis like that. So as we plot, so this one will represent 10, 20, 30, 40, 50. No, this one we take 20, 40, 60, 80, 100, and this one will be 5, 10, 15, 20, 25. So the y-axis will be having 1 square to represent 20 meters, and the x-axis will having 1 square to represent 5 seconds. So we can plot our points like that. So if we plot our line, we are plotting a curve. As you can see, the curve is not straight. That means that this is the distance time graph of the body that is moving with an uniform but increasing speed.